Music nice. Yeah. You're definitely gonna want to wear your heavy stuff. Oh, I know. It's cold when daddy opened the door. What else is she? Did you like this food? Thank you. And we're gonna go to. Well, we're gonna go do work. And then around noon, you'll come visit me. Guess where Anna is?
Yeah, see,
On top of my legs. One spot. One spot. Sitting with this so myself confused was. Yeah.
And Susie, would you grab me one of those?
Oh.
You look cute in
It's well, it looks cute.
That's the way I wear it with boots and tights, and you got the prettier necklaces and stuff that I don't have, but it just she does look good. You did.
Okay, folks, I show that it is 8 o'clock and we've got a lot to cover, so I'm gonna go ahead and get started. Today what we're gonna be doing is we're gonna be starting our chapter on energy. So we've discussed balancing a chemical reaction. We've discussed how to determine the state of matter of the reactants and the products. But if we're going to properly discuss a reaction, you've got to discuss everything. I mean, a reaction is kind of like a story to a chemist. So a story needs to include a lot of detail. And one piece of detail that we haven't discussed yet is the energy associated with the reaction, because every reaction has some sort of energy associated with it. Now, energy. Energy must follow the law of conservation of energy, which basically says that energy cannot be created. Nor destroyed. So that means that so when we start thinking about energy, we've got to think of the system and we've got to think of the surroundings. Because if energy flows into the system, it has to come from the surroundings. And if energy leaves the system, it has to go out to the surroundings. Now, before we get into the individual pieces, let's talk about what is the system and what is the surrounding. For a chemical reaction, the system is the reactants, and the products. Everything else is the surroundings. So the surroundings include the water the reaction occurs in. It includes the container that the reaction occurs in. It includes the air surrounding the reaction. It includes anything we put in there, such as a thermometer to read the temperature change. Basically, anything that is not the system is the surroundings. So, again, energy, we've got to talk about energy if we're going to finish telling the story about a chemical reaction. Energy must follow the law of conservation of energy, which says energy cannot be created nor destroyed. So basically, we have to think of energy in terms of both the system and the surroundings to completely understand what's going on. Because if energy enters into the system, it has to come from the surroundings. If energy exits the system, it has to go into the surroundings. The system is going to strictly be your reactants and your products. It does not include the water that the reaction occurs in. It does not include anything about the container or the air that surrounds the reaction. It is simply the reactants and the products. Everything else constitutes the surroundings. Now, something that we need to talk about is signs of energy. A positive energy for our purposes means that energy enters into, or energy of the system increases. And negative energy means that energy of the system decreases. In other words, for our purposes, the sign simply reflects the direction that the energy flows. So if it's leaving the surroundings and entering the system, it's going to be a positive energy. Where if it's leaving the system and entering the surroundings, it's going to be a negative energy, because again, we're looking at how the energy changes. So basically, the delta E, the change in this energy, will reflect how the system changed overall. And it's basically this energy that enters in the system, you take that into account, as well as the energy that exits the system. Any questions over this concept of energy? If so, you can unmute yourself or put it in the chat, either one. Okay. So the next thing we're going to talk about is going to be the specific heat. Everything can absorb a certain amount of energy before you see a change in temperature. The specific heat related, which is represented with a lowercase c, indicates how much energy can be absorbed before the system increases by 1 degree Celsius. Specifically with this system, we're talking about its mass. For example, let's see. For example, gold has a specific heat equal to 0.13 joules per gram degrees Celsius. So in other words, it can absorb 0.13 joules of energy to change 1 gram of gold by 1 degree Celsius. Whereas water has a specific heat of 4.184 joules per gram degree Celsius. So it can absorb 4.184 joules of energy to change 1 gram of water by 1 degree Celsius. This is one reason they say a watched pot never boils, is because it's water takes forever. It takes a lot of energy to get it up so that it'll increase by 1 degree Celsius. It takes a lot of energy to get that 1 gram of water to boil. And if you're talking a full pot, you're talking about a lot of grams of water. So it takes a lot of energy to get just the pot to go up 1 degree. So that's why they say a watch pot never boils. Okay, so we can talk about the heat Q needed to increase the mass of a system by a change in temperature. And to do so, that equation is Q is equal to MCAT. So you have Q, which is heat, M, which is mass, C, which is the specific heat, and delta T, which is T final minus T initial. Now it is this heat, so heat is a unit of energy. So we will apply our positive and negative depending upon whether we're adding heat to the system, so heat is absorbed, or whether heat is generated by the system, heat is given off. Let's look at some examples. What is the specific heat of aluminum if the temperature of a 28.4 gram sample of aluminum is increased by 8.1 degrees Celsius when 207 joules of heat is added. Okay, let's talk about what we've been given, because that's important so that you recognize what formula you're definitely wanting to use. We have been told that we have a 28.4 gram sample. So in other words, we know the mass is equal to 28.4 grams. We have been told that the temperature increased by 8.1 degrees Celsius. So in other words, our delta T is 8.1 degrees Celsius. We have been told that we have 207 joules of heat is added, and I do stress the word added. So that means our Q is equal to a positive 207 joules. And we were asked to solve for the specific heat. So in other words, we want to solve for C. So if you look at this, you can see that you're going to use Q equals MCAT. And to solve for this, we're going to divide both sides through by M delta T to get our C. So 207 joules divided by our mass of 28.4 grams times 8.1 degrees Celsius is going to equal the specific heat of aluminum. And the specific heat of aluminum comes out to be 0.900 joules per gram degrees Celsius. Let's look at another example. How much heat must be added to a 8.21 gram sample of gold to increase its temperature by 6.2 degrees Celsius? The specific heat of gold is 0.13 joules per gram degrees Celsius. Okay, so let's look at what we were given. We were told we have an 8.21 gram sample of gold. So in other words, our mass is equal to 8.21 grams. We were told that the temperature increased by 6.2 degrees Celsius. And yes, I'm highlighting which direction the temperature is going because that does make a difference. So our delta T is equal to 6.2 degrees Celsius. We were told that the specific heat of gold is 0.13 joules per gram degree Celsius. So that C is equal to 0.13 joules per gram degree Celsius. And we were asked to solve for the heat. So in other words, we want Q. Again, by listing out what you were given, you can see you need Q equals MCAT. But in this particular case, we're solving for Q. So we're gonna just leave the equation as is. So Q is equal to 8.21 grams times the specific heat of 0.13 joules per gram degrees Celsius times a temperature of 6.2 degrees Celsius. You will notice that the units degrees Celsius cancel out, as do the units of gram, leaving you the unit of energy, which is that of joules. So Q comes out to be equal to 6.6 joules. Because it is positive, it means that heat is added. Which this is a good thing you can check, because if heat's added, that means temperature had to go up. If heat's removed, that means your temperature has to go down. So that's kind of something you can look for to help you identify what's going on. Again, if heat's added, the temperature must go up. If heat is removed, the temperature must go down. And so the signs will help you a little bit in that regard. My first two examples I gave you were strictly about the system. The surroundings didn't come into play, but keep in mind that Q of the system, but keep in mind those two things have to be together. So if, let's go back to this whole idea of the system. And the surroundings. And the law of conservation of energy. If we add energy to the system, this means that the system's energy would go up. But at the same time, it means that the surroundings energy has to go down. Because again, we've got to follow the law of conservation of energy. So if one goes up, the other one has to go down. For that reason, we can write another equation where Q of the system is equal to a negative Q of the surroundings. And to be quite honest, I could have also written it as a negative Q of the system equals a positive Q of the surroundings. In other words, it does not matter which one I claim as positive and which one I claim as negative. It's just they're going to be opposite in sign. They're going to be the exact same value, just opposite in sign. Again, they're going to be the exact same value, just opposite in sign. And in fact, we used that piece of the puzzle last week in lab, because you calculated Q for the surroundings and it came out to be a positive value in that third from the end column on your calculations. But then the system was a negative value, but it was the exact same number, just opposite in sign. And that is because energy cannot be created nor can it be destroyed. So if we write Q of the system equals negative Q of the surroundings, and Q equals MCAT, then what we can say is Q is MCAT of the system equals a negative MCAT of the surroundings. And now we have a formula that describes the transfer of energy. Any questions so far? I'm going to give you a moment to catch up on all the writing, and then I want you to take a moment to look at everything and see if it's making sense. So I just want to recap up to this point. Energy cannot be created nor destroyed. Heat is a form of energy. So heat cannot be created nor can it be destroyed. If it leaves the surroundings, hence a negative Q, that means it has to be absorbed by the system, hence a positive Q. Q is the heat of anything can be described using the equation MCAT, where you have the mass times the specific heat times the change in temperature. It really doesn't matter who is positive and who is negative as far as the equation is concerned, whether the system is positive or whether the system is negative. What matters is that the system and the surroundings are opposite in sign, but they will be the exact same value. So let's look at one of these questions with a heat transfer. A 2.50 gram sample of zinc is heated, then placed in a calorimeter containing 65.0 grams of water. The temperature of the water increases from 20 degrees Celsius to 22.50 degrees Celsius. The specific heat of of zinc is 0.390 joules per gram degrees Celsius, and water is 4.184 joules per gram degrees Celsius. What is the initial temperature of the zinc metal? Now, one thing you do need to note is that before we can answer this, is that heat is transferred from the hotter object to the colder object until the two objects reach the same temperature. So basically what that means is that the T final for both objects will be the same. Okay, with that in mind, let's look at what we were given and what we have to work with. So we were given a 2.50 gram sample of zinc. And it was placed in a calorimeter containing 65 grams of water. The temperature of the water increases from T initial of 20.00 degrees Celsius and T final of 22.50 degrees Celsius. The specific heat of zinc is 0.390 joules per gram degree Celsius. And the specific heat of water is 4.184 joules per gram degree Celsius. Because of the note, that means that the T final for our zinc is also going to be 22.50 degrees Celsius, because the T final for both must be the same. And then we were asked to solve for the initial temperature of the zinc metal. So we want T initial for our zinc metal. When I make out my list, what I notice is that I have two substances. So I'm going to be using Q of the system is equal to negative Q of the surroundings, which in this case would be Q of zinc is equal to negative Q of water. And we know that Q is equal to MCAT, so we're talking about MCAT for zinc is equal to MCAT, a negative MCAT, excuse me, for water. And that is actually, I'm glad I made that mistake, because that is actually the most common mistake that students do, is they forget the negative sign. Don't forget your negative. So plugging what we know in. Oh, and the other thing that we know is delta T is T final minus T initial. So we can write that out. So this becomes MC T final minus T initial for zinc is equal to a negative MC T final minus T initial for water. So plugging in what we were given, we have the mass of our zinc is 2.50 grams. The specific heat of the zinc is 0.390 joules per gram degree Celsius. T final for zinc was equal to 22.50 degrees Celsius minus T initial, which is what we want to solve for. All that is equal to a negative mass for the water of 65.0 grams times the specific heat of water of 4.184 joules per gram degree Celsius times the T final, which was 22.50 degrees Celsius minus T initial of 20 degrees Celsius. So 2.5 times 0.39 is 0.975. The grams cancel here to get joules per degree Celsius times 22.50 degrees Celsius minus T initial. That's equal to negative 65 times 4.184, a negative 271.96. Again, at this point, I've got the grams canceling to leave me joules per gram degrees, joules per degree Celsius times 22.50 degrees Celsius minus 20.00 degrees Celsius. Continuing this out, you've got to do some multiplying through. So I'm going to multiply that 0.975 by the 22.5 and that 0.975 by T initial. And you've got it, it comes out to be 21.20, 21.9375. And that is joules minus 0.975 joules per degree Celsius times T initial equals, and we can finish out this. So 22.5 minus 20 is 2.5 times a negative 271.96 is a negative 679.9. And that's going to be joules because our degrees Celsius will have canceled out when we multiplied it through. Moving everything around by subtracting out the 21.975. I mean 9375. You get a negative 701.8375 joules is equal to a negative 0.975 joules per degree Celsius times T initial. Dividing both sides through by that negative 0.975, you get 719.8 degrees Celsius. Now I'm going to quickly check on my work to make sure I didn't make a mistake. And it looks correct. So I would report my T initial as if I were doing it, if you're worrying about significant digits. T initial comes out to be 720 degrees Celsius. Okay, questions? You can put them in the chat or you can open your mic and ask the question. You have 2 ed puzzles due next Sunday or this coming Sunday. Or is it Monday? You have 2 ed puzzles either Sunday or due Sunday or Monday. I cannot remember which. That is over Q equals MCAT, as well as Q of the system is equal to Q of the surroundings. So I separated these last 2 topics, and you have 2 different ed puzzles related to it that are due either Sunday or Monday. I cannot remember. Any questions? Okay, if there are no questions, then we're going to move into enthalpy. Enthalpy is often referred to as the heat of the reaction. Now, when we start taking into account a reaction, unlike the zinc example that I just gave you, where you could physically measure the temperature of the zinc and you could physically measure the temperature of the water, when you're talking about a chemical reaction, you can't measure it as easily. So we start talking about the enthalpy of the reaction. And the enthalpy of the reaction is related to the heat of the reaction as Q of the reaction divided by the moles of the material. And that gives us our enthalpy. And enthalpy is represented by a capital H. Now, enthalpy is a state function. State functions do not rely on the path between the starting point and the ending point. It simply relies on the identity of the starting material, the identity and quantity, of the starting material, and the identity and quantity of the ending material. Now, I would suggest, because I would suggest watching the videos in totality that I assigned for today. And the reason I'm doing that is because I'm summarizing different pieces that are related to things you need to know, that are related to things that are going to be directly applicable to the mathematics. But if you want to truly understand what's going on, you need to watch the videos, because I'm getting to the nuts and bolts today rather than introducing the topic in totality. Okay, so again, enthalpy is the heat of the reaction. It is represented with capital H. Anytime you see a capital letter, oftentimes that means that it's a state function. A state function does not rely upon the path between the starting point and the ending point. It simply relies on the identity and quantity of the starting material and the identity and quantity of the ending material. The enthalpy of the reaction can be calculated as Q of the reaction divided by the moles. So again, if you look at what I just said, it's dependent upon the identity and the amount. That's where that moles comes into play. And it's called the heat of the reaction because it involves the heat, the form of energy that is known as heat. So that's why it's called the heat of the reaction. Now, let's talk about this enthalpy. And what we're going to do is we're going to talk about, so let me just look at let us just look at an example. Let's say I have the equation C2H6, so in other words, ethane, in the form of a gas, reacting with 3.5O2 gas to form 2CO2 gas plus 3H2O gas. This particular enthalpy is equal to a negative 1560 kilojoules. But if I reverse the reaction, so that I am taking a CO2 gas and combining that with water gas, then we get C2H6 gas plus 3.5 oxygen gas. Now the enthalpy is equal to 1,560 kilojoules. I want to make note of two things. Number one, the enthalpy is directly related to the identity of the reactants and the identity of the products. If I change the state of matter of any of these substances, I will change the energy associated with that substance. Or I should say, I will change the enthalpy associated with that substance. So if I change the state of matter, I'm going to change the enthalpy of the substance, which is going to change the enthalpy of the reaction. So that's the first thing I want you to note, is that change the state of matter and you change the enthalpy. The second thing I wanted you to note is that if you reverse a reaction, simply change the sign. Of the reaction. That goes back to this whole idea of a state function that I mentioned earlier. It depends upon the identity of the starting material and the identity of the ending material and quantities. But as long as you've got the same materials in the reaction, then if you flip the reaction, you're going to have the exact same you're going to have the exact same enthalpy, just opposite in sign. Let's look at another something. Let's go with let's go with 2NH3 gas decomposing to form N2 gas plus 3H2 gas. This reaction has an enthalpy of a positive 91.8 kilojoules. In other words, you got to add 91.8 kilojoules to the reaction in order to make it occur. Now, if I double this reaction, I will double the enthalpy so that it is now 183.6 kilojoules. So the thing to note here is that I multiplied this original equation by 2 to get the result. So whatever you multiply an equation by, you multiply that delta H by the same number. Again, this comes back to this state function idea. It is all about the identity and the quantity. So here it is about the quantity. Any questions so far? Okay. The last thing I want you to note about enthalpy is if you add reactions together, to get the desired reaction, then the enthalpy will be the sum of those reactions. So an example, let's take 4NH3 gas going to form 2N2 gas plus 6H2 gas with its enthalpy of a positive 183.6 kilojoules. And we'll do 2 N2 gas plus 2 O2 gas going to form 4 NO gas with a delta H of negative 361 kilojoules. And we'll combine that with 6H2 gas plus 3 O2 gas going to form 6 H2O gas with an enthalpy of negative 1360 kilojoules. Then when I add this together, basically what we're doing is if things appear on one side of an equation and it also appears on the other side of the equation, you can get rid of it. So in the first equation, there's no other place for NH3, but when we get over to the N2, there's 2 N2 gas on the product side of the first reaction, and there's 2 N2 gas on the reactant side of the second equation. There is 6H2 gas on the product side of the first reaction, and there is 6H2 gas on the reactant side of the third equation. Because those appear in multiple equations, we can cancel them out. You cannot cancel out the O2, however, because the O2s both appear on the reactant side. So they will simply add together. So when you add this reaction together, it's 4 NH3 gas plus 5 O2 gas going to make 4 NO gas plus 6 H2O gas. If you add those reactions together, then to get the delta H, you're simply going to add the delta H's together and you get a delta H of let me make sure I got all this number right. You get a delta H of a negative 1537.4 kilojoules for that new reaction. So what are the take-homes from this newest part? Well, I've highlighted them in blue as I was writing. The first is that if you go back to the state function, it is directly dependent upon the identity and the amount. When we're talking about the identity, it means that the state of matter is important. If you alter the state of matter of anything within the reaction, you will alter the enthalpy for that reaction. The second thing that I stated that was of importance is that if I reverse a reaction, because the identity and the quantities remained constant, they were simply flipped, then all I need to do is reverse the sign of the enthalpy and change it from either a positive to a negative or from a negative to a positive, whichever one applies. The third key takeaway is that if you multiply an equation by some coefficient, then you also need to multiply the enthalpy by that coefficient. Because again, this comes back to the state function where the identity and the quantity matter. The last takeaway is that if you add reactions together to get a target reaction, then to get the enthalpy of that target reaction, you simply are going to add up the enthalpies of those sub-reactions. Any questions? So today has been a quick introduction of a variety of concepts. The very first one is the flow of energy. Energy cannot be created nor destroyed. So if the energy of the system increases, that means that the energy of the surroundings had to decrease. We represent the flow of energy with signs. A positive energy means that the energy flowed into that material, that system, or the energy flowed into the surroundings if we're looking at the surroundings. Whereas a negative means that the energy flowed from the system, or if we're looking at the surroundings and we have a negative surroundings, it means the energy flowed from the surroundings. Q is heat, and heat is a form of energy. We can calculate heat using Q is equal to MCAT, where M is the mass of the object, C is the specific heat for that object, and delta T is the change in temperature that that object undergoes. One thing I did forget to mention about specific heats is specific heats are looked up in tables. So you will either be given the specific, well, you will be given the specific heat, or you can look it up in a table. For an exam, you will be given the specific heats. But on homeworks and stuff like that, if you're not given the specific heats, you can look it up in a table. Following on with this heat is a matter of flowing from the system to the surroundings or vice versa. We can take that Q equals MCAT and we can talk about that heat flow as Q of the system is equal to negative Q of the surroundings. The value is the same. The only thing that will change is the sign. And then because Q equals MCAT, we can substitute MCAT into the Q of the system is equal to negative Q of the surroundings, so that we get MCAT of the system is equal to negative MCAT of the surroundings. And so now we're talking about that energy flow. Heat is related to the enthalpy of a reaction. The enthalpy of a reaction is equal to the heat of the reaction divided by the number of moles. That is because enthalpy is a state function that is dependent upon the identity of the materials and the amount of materials, and hence the reason we have to include that piece of information. And then we talked about enthalpy, and we talked about how to look at the enthalpy of one reaction and how it impacts the enthalpy of the reverse reaction. We looked at how to take the enthalpy of one reaction, and if we multiply that reaction by a coefficient, how the enthalpy of the new reaction can be generated. And we also talked about if we add up sub-reactions to form a target reaction, then the enthalpy of the target reaction will be the sum of those sub-reactions enthalpies. Any questions about today? Well, I appreciate being able to Zoom with you today so that I could spend more time with my daughter. Actually, so I could spend time with my daughter who lives out in Amarillo, Texas. If I'd have been in person today, I would not have been able to come to Amarillo to visit her because of the length of travel. So I do appreciate being able to Zoom with you today, and I hope everybody has a very good Thanksgiving holiday. The only thing that you have due, if I'm not mistaken, is you have those 2 videos that are due. But otherwise, I don't think you have anything due this week. No active for this week. You get the day off on active. Any other questions for me? I will hang on because we've got 3 more minutes of class. If you have questions, you can stay on and ask. If not, we are done for the day. And I, again, hope you have a wonderful Thanksgiving holiday. I will see you on Tuesday.